Right, let's just dive straight into this. Welcome to today's Explainer, where we are going to unpack the genuinely fascinating mechanics of chilled water systems. Grab your lab coats, because today we're running an experiment. We're absolutely not here to prescribe a specific control strategy or tell you how to run your plant. Actually, we're just observing. We want to see exactly what happens inside the pipes and the chillers when different design and control decisions hit a constant cooling load.
So, here's our quick roadmap for the lab today. First up, setting the baseline. Second, Scenario 1, temperature reset. Third, Scenario 2, higher delta T. And finally, the core system relationships.
Let's kick things off with Section 1, setting the baseline. To really understand these shifting variables, we first need to ground ourselves in a completely controlled, closed-loop setup. And here is our anchor for today. 500 tons. I really want you to cement that number in your mind. In every single example we run today, the cooling load is strictly held at exactly 500 tons. Why? Well, keeping the load totally constant is literally the best way to isolate cause and effect. We're locking this down so we can observe exactly how temperature differences and water flow interact without the distraction of a fluctuating building load.
Now, you might be wondering how the equipment actually sees this. Here's a kind of wild truth about real-world operations. The chiller doesn't inherently know that the building load is 500 tons. There's no magic dial telling it the overall tonnage. It only responds to control signals. It's constantly scanning coil valve positions, supply and return temperatures, just looking for clues to figure out if it has unused capacity. And honestly, that perfectly sets the stage for our first experiment.
Moving right along into Section 2, Scenario 1, temperature reset.
Let's see how this all builds into real-world mechanics by observing what organically happens when a control system suddenly decides to raise the supply temperature. It's like a giant domino effect, so think about how this plays out. Imagine our starting point is a traditional 10-degree temperature difference. Suddenly, the control system sees stable zone temperatures, it sees valves that aren't wide open, and it registers available capacity. Boom, step 1. The system automatically resets the chilled water supply temperature upward. But wait, as that supply water gets warmer, each gallon naturally carries less cooling capacity. So step 2, the control valves are literally forced to open further to maintain our strict 500-ton output. Step 3, with a smaller temperature difference across the coil, way more water is required to move that same amount of heat, so system flow shoots up. And finally, step 4, because flow is up, pump energy rises to physically push all that extra water.
So, what does this all actually mean? Well, there's a quote directly from our source material that really hits the nail on the head. Energy is not eliminated, it is redistributed within the system. By resetting the chilled water temperature, we kept our capacity by bumping up the flow. But it's a mechanical trade-off, right? We are basically trading increased pumping energy for reduced compressor lift. The compressor just doesn't have to work nearly as hard because the chiller is now seeing warmer entering water, which can actually improve the compressor's efficiency.
All right, on to Section 3, Scenario 2, higher delta T.
Let's completely wipe the slate clean and shift our focus. Our two experiments perfectly illustrate this contrast. Scenario 1, the one we just did, was a reactive control adjustment. The system basically guessed based on available capacity and reacted on the fly. Scenario 2, however, is a completely proactive design decision. In this setup, the flow drops specifically because of a system parameter that was baked into the coils from day one. Let's break down what that looks like.
In this specific design, the coils are built from the ground up to operate with a larger 15-degree temperature difference, or delta T. We are still delivering the exact same 500 tons, but because of this upfront design decision, we're doing it using significantly less water. The chiller now sees warmer return water and lower evaporator flow. It hits the exact same 500-ton target, but it pulls it off by moving fewer gallons rather than demanding colder water. And as you'd probably guess, because the flow is lower, pump energy drops. This is honestly one of the absolute biggest motivations for designing high delta T systems in the first place.
Which brings us to Section 4, the core system relationships.
Having successfully run both of our scenarios, let's clearly define the universal laws we just proved in the lab. When we look at the numbers, the difference in required flow is stark. To meet our 500-ton load at a 10-degree delta T, we required roughly 1,200 gallons per minute. But when we bump that to a 15-degree delta T, the required flow plummets to just 800 gallons per minute. Think of it using a simple heat bucket analogy. Imagine every gallon of water is a bucket. A larger delta T just means each individual bucket is physically carrying a much heavier load of heat. Because each bucket is pulling its weight more effectively, you naturally need way fewer buckets to do the exact same 500-ton job. The cooling load didn't change a single bit, only how the heat was transported changed.
Now, let's flip the script for a second. I want you to really think about this. Based on everything we've just seen, what happens if the water flow changes, but our cooling load remains stubbornly fixed at exactly 500 tons?
Yep, you guessed it. The temperature difference absolutely must automatically adjust to compensate. If the flow increases while the load stays exactly the same, the temperature difference is forced to decrease. If flow decreases, the temperature difference has to increase. There's no way around it. It is automatic, unavoidable physics. The mechanical system will always balance flow and temperature difference to satisfy that fixed load.
Let's just slow down for a minute and lock in these golden rules of chilled water system behavior that we've mapped out today. First, when the load is fixed, your delta T strictly dictates your required gallons per minute. Second, any arbitrary change in flow will forcibly shift your delta T. The reality is, in a chilled water system, load, flow, and temperature difference are permanently linked together. If you mess with one while the load is fixed, the others are mechanically forced to respond. These variables are literally inseparable.
You know, we didn't run these scenarios today to tell you which strategy is definitively better, but rather to give you a clear, unobstructed view of how the machine actually breathes. Understanding these automatic trade-offs, like swapping pump energy for compressor efficiency, gives you just incredible insight and control. So as we wrap up this explainer, I'll leave you with this final thought. How will the inseparable links between load, flow, and temperature reshape your next system design? Thanks so much for stepping into the lab and diving deep into the mechanics with us today. Keep learning and keep exploring.